Welcome to the Explainer. Today, we're going to unpack a really critical standard, one that keeps our most complex devices, everything from huge data centers to the tech in your car, running reliably. We're talking about a low-level language that makes sure updates happen safely and that every piece of hardware speaks the same dialect, no matter who made it.
So just think about this for a second. The firmware in a device, that's its brain. It's the most fundamental software it has. So trying to perform surgery on that brain while the system is running or even just getting ready to run, well, it's incredibly risky. One little mistake, one scrambled bit of data, and you've just created a very expensive paperweight. So the question is, how do you get it right? Every single time across maybe thousands of different devices.
Well, before we had a standard like PLDM, the world of firmware updates was, to put it mildly, just pure chaos. I mean, every single hardware company had its own special tool, its own secret handshake, just to update its own devices.
And this slide just lays out the difference perfectly. On the left, you've got the old way. It was a total mess. You needed a specific tool from vendor A for their network card, a totally different one from vendor B for their storage controller, and chances are they only worked on a specific operating system. It was fragile, super inefficient. Now, look at the right. This is the PLDM way, a universal language. It's a common method that works completely outside of the main OS, often before the computer even boots. It makes the whole thing predictable, orderly, and just incredibly reliable.
Okay, to really get how this all works, we need to meet the two main actors in this play. And to make it stick, we're going to use an analogy from space exploration that I think is just perfect. We've got mission control, and we've got a rover on a distant planet.
First up is the Update Agent, or the UA. This is our mission control. It's the central command, usually living inside a management controller on a server, that runs the whole show. It's holding the new software, and it directs the entire update from beginning to end.
And this is our rover. It's the firmware device, or FD. This is the actual piece of hardware out in the field that's about to get that brain upgrade. Could be a network card, a storage controller, really any smart component. It's the one getting those critical instructions from mission control and then carefully performing the update on itself.
So, how do mission control and the rover actually talk to each other? You might think it's just a one-way street, where mission control just beams down all the data at once. But no, it's so much smarter than that. They follow this precise 7-step dance, a really careful back and forth to make sure everything goes off without a hitch. Let's walk through it.
Now, what's so cool about this is how it breaks down that conversation. Mission Control kicks things off, saying, hey, get ready for an update. Then it sends over a manifest, basically a list of all the parts. But look closely at step 4. This is the key. The rover actively pulls the data it needs, piece by piece. It's in control. It says, okay, send me the next chunk. It takes that data, it checks to make sure it's not corrupted, writes it to its own memory, and only then does it ask for the next piece. This pull model is absolutely crucial for reliability. After all the pieces are there, Mission Control gives the final go command to activate, and then it checks in to make sure the rover's up and running on the new software.
But with all this back-and-forth communication, what stops it all from turning into a mess? What prevents the rover from asking for data when it should be checking it? Or Mission Control from trying to activate a half-finished update? Well, that is where the real genius of this whole system lies. It's all governed by a strict set of rules called a state machine.
And here's the main takeaway, the most important part of this whole thing. The firmware device can't just do whatever it wants, whenever it wants. It has to follow this rigid set of rules based on its current state. Think of it like a board game. You can only make certain moves depending on which square you're currently on. That structure, that's what makes the entire process so incredibly robust.
So this table gives us a kind of simplified look at that board game. The rover starts off in the idle state, just waiting. The only way it can move to the next state, ready exfir, is if it gets a request update command from Mission Control. Once it's there, it's waiting for a different command, update component, to start the transfer. And while it's in the exfir state, all it's doing is pulling data. It can't do anything else. You see how it works? Every step is like a locked room, and you can only get out by using the exact right key, which is a specific command. It ensures everything happens in perfect sequence.
And this quote, right from the official spec, just perfectly illustrates the core safety feature. Once Mission Control sends that very first request update command, the rover basically puts up a virtual do not disturb sign. It enters this lockdown update mode. It will flat out ignore any other update requests until this one is either finished successfully or it's been officially canceled. This is what prevents conflicting commands from causing total chaos.
So we've been deep in the technical details. Let's pull back up for a second. What's the big payoff here?
How does all of this come together to create a more stable, more manageable world for all the complex systems we depend on?
So at the end of the day, by defining these clear, universal rules, PLDM creates this trusted framework for one of the most sensitive things you can do in a system. The state machine gives you incredible reliability. The standardization means you get interoperability, no more being locked into one vendor's tools. The verification steps give you security. It makes everything simpler by taking the main OS out of the picture. And finally, it lets you coordinate. A system can update 10 different parts from 10 different vendors and then activate them all together on the next reboot. It literally brings order to the chaos.
Which kind of leaves us with a final thought to chew on. PLDM brought a universal language and a strict rulebook to the Wild West of firmware updates. So, as our technology gets even more interconnected, even more complex, what's the next frontier? What's the next critical, chaotic process out there that is just crying out for its own universal language to make it safe and reliable for everyone?